Okay, so welcome to the second video on continuity. So basically what we just did was kind of understand the idea of a function being continuous, that I could draw the graph without any breaks or holds in a smooth way. And also we interpreted that in terms of limit statements. So now we're just going to do a couple examples where we practice what we just learned. So for this problem, we're going to be looking at the given graph. And for the first part, we're just going to identify the x values at which there are discontinuities. So we can kind of see that this graph has a couple of situations where it's not continuous, right? Like right here, and right here. Other than that, the rest of the graph is smooth and I can draw it without having to pick up my pen. And so we're talking about the x values that correspond to, I kind of just like did blobs, but so we're talking about this x value, and this x value. So first, to just identify the x values, it would be x equals -1, x equals 0, and x equals 1. These are the three x values for which the function is not continuous. Okay? Now, for the next part, we want to explain explicitly by showing the exact part of the definition that fails and explain why or how the definition of continuous is not satisfied for these x values. And I wanted to recall that the definition of continuous states that y equals f of x is continuous at x equals c if and only if the limit as x approaches c equals f of c. So that means the two-sided limit, the left and the right limits. So if we begin with x equals -1, we can see that this is a jump type discontinuity. But if we just want to kind of look at that definition, right, it's telling us like we have three things to compute, and as soon as two of those things are not equal, or maybe one of those things doesn't exist, we have our reason. So for x equals -1, if I take the limit as x approaches -1 from the left of this function, let's call it f of x. So as x comes in from -1, y is approaching 3, right? So we can see that on the graph here. As x is coming in towards -1, the y values are getting closer and closer to 3. Okay, on the other hand, the limit as x approaches -1 from the right now, so instead if I come in from the right, it seems to be approaching a number slightly less than 1. So let's say maybe like about 0.8 approximately. And so because these two numbers are different, what we can conclude is that the limit as x approaches -1 of f of x does not exist. And so that would be a reason why the function is not continuous, because 3 doesn't equal to 0.8. Okay? So yeah, we can just also kind of say like that these are not equal, so that it fails the definition. So I can write that nicer maybe. Right? So because 3 does not equal to 0.8. So that's the first reason why the function isn't continuous at x equals -1. We can also consider x equals 0. So when I have this, there's different things you can do. You can compute the limit as x approaches 0 from the left, the right, but for me the easiest thing is I actually see that 0 is not even in the domain of the function. Let me erase some of the marks that I've made so that it's easier for you to see it again. So if you look at the graph of the function, 0 is not even in the domain of the graph. So the easiest reason for me why this function isn't continuous is that f of 0 does not exist. And so therefore, the function definitely is not continuous at 0. Okay, and then for the last one, x equals 1, well, This is a removable type discontinuity, and so even though the limit as x approaches 1 from the left and from the right of this function exists and equals 1, it's also the case that f of 1 is equal to 2. And so because 1 doesn't equal to 2, the function is not continuous. If the function were to be continuous, I would require those two values, the limit as x approaches 1 of f of x and f of 1, to be the same. So this is how you can mathematically justify using the definition in terms of limit statements why the graph of a function fails to be continuous at a point. Okay? So, sometimes I give you only the graph and no equation, and other times I give you only the equation and no graph. Okay, so we would like to see a problem like that as well. So this is problem 8, which is just asking where is the given function continuous. So this function is f of x equals the square root of x plus 6. So this is almost like a domain type of question, because I know that I can't take the square root of a negative number. And if you want to, if you like having graphs, you can always bring the graph into the picture. We know from pre-calc that this is the same as the graph of the square root function, but shifted horizontally over to the left by 6 units. Or, you could just put it in your graphing calculator. So this is what the function looks like. And we can see that this function will be continuous on its entire domain. So for all the values of x for which it's defined, but for values of x that aren't in the domain, then the third condition, f of a exists, is not met. So what we can say is that this function is continuous on its domain, which is the set of all x where x plus 6 is greater than or equal to 0, which means x is greater than or equal to negative 6, right? So in conclusion, this function is continuous on the closed interval from 6 to infinity. So it's continuous on its domain. So that's just a function given by an equation that you're familiar with. And then we could also have a function such as the function in B, which is a piecewise function. So this is the function h of x equals x plus 2 times x minus 3 all over x minus 3 if x is not equal to 3. We'll sketch it soon. And the question is, for this function, is the discontinuity removable? If so, what is the continuous extension? So first we're going to find out where it's continuous, and then we'll go further to answer about the type of discontinuity. So what you can see about this equation is that basically x minus 3 over x minus 3 will cancel as long as x is not equal to 3. And so the graph of this function, it looks the same as the graph of y equals x plus 2. It's just that it's going to have a hole at 3 because 3 is not in the domain of this function. Okay, so to put that into a picture, we're talking about the graph of y equals x plus 2. So I know that 2 is the y-intercept, okay, and then I know that the slope is 1. And I am supposed to pay attention to the point where x is equal to 3 to put a hole in it. So at 3, it's going to be there. Sorry, let me make the hole a hole. So this is my shaky line. This is supposed to be the graph of the linear function. So this is the graph of h of x. Again, it's the same as the graph of y equals x plus 2, but x can't equal 3. Okay, so there's a hole in the point 3 because that's not in the graph of the function. So we can first of all say that the function is continuous everywhere except x equals 3, because 3 is not in the domain of h. So I believe that was the first question, was where is it continuous? And the second question, is this a removable discontinuity? And if so, what is the continuous extension? So it's removable if you can redefine the function at just one point to obtain a continuous function. And we can, right? The continuous extension of this function is just the line y equals x plus 2. Like, we can see that. All we have to do to make it be continuous is plug the hole in to color that in and make it black so that I would have this blue line. And I can say that symbolically as follows. So what we would say is that, yes, the discontinuity is removable. And the continuous extension, which means the equation of the plugged hole graph, basically. So, and the continuous extension is y equals x plus 2, okay, the blue line. So this is just like a more specific example about removable discontinuities. I believe you might see some in the homework on my math lab that are similar to this. So yeah, so that's the end of the lesson that I have for you about continuity.